Interesting. All right. Sorry, man. I'm like sweating up here. All right. Well, how many of you watched my orientation video? Okay, so some of you haven't. All right. Here's the way this is going to work. Let me just talk through it instead of getting going and showing you everything. We have a website that you get into through ACES, right? You log in, you get to a place called Canvas. How many of you have done that? Okay, if you have not done that, you need to do that. There's a video that you can watch that kind of runs through what the syllabus is about, things like that. So we can get right into the work today. But this is the way it's going to be. I'm going to be up here. I'm going to be writing down all the math. It's going to be projected here. It's going to be recording. And then I'll push that out to YouTube, and then you can watch it later if you want. Okay, it's not a substitute for being here. You still have to come to class, but it's always something you can go back and watch if you need to. Okay, I do have to take attendance. It's not something I want to do. It's something I have to do. I know if this were a large university, you'd probably just show up when you want to show up, and then talk to a friend who was in class or whatever. But here, we have to be accountable for who was here when they are here. You get 2 absences in this class because each class is really worth like 2 fall or spring semester courses. So we're here for what, 3.5 hours? It's a long class, right? So this is the way it'll go. I want to kind of get you acquainted with the software I'm going to be using, and open this sucker up here. There we go. So I'll be going through the notes like this, and that's pretty much what you have in front of you. All right, anyone need to sign in? And then as I write things down or say things, you can write on the notes that I provided you. All right? Now, this class, the way that this is set up is that our goal is to finish this book, which, again, is in your syllabus that you can go research and buy. If you have an electronic copy, that's fine. I'm not going to require you to ever really sit in class and open the book and do a problem out of it. So, how you attain this, if it's electronic or hardback, that's really up to you. But I will assign homework out of it, all right? So what I'll do is I'll come up here, I'll lecture, and then I'll give you homework problems. You go home, you do those problems. It's assumed that by the next class you've completed that homework set, all right? So even if it's only 2 days later, the assumption is that you've done that. Now, for summer class, it's a lot of work, okay? You need to be prepared for that because I do expect a lot from my Cal 3 students. I will give you 8 take-home exams this semester, all right, this summer. That means 1 per week. The problems on my take-home exams are not like problems out of the book, all right? So you're not going to be able to just say, oh, that's just like the problem in the book. I just do it like that. It's an extension of what I do in class. So if I ask you to, we'll do some pretty basic problems in here, just get the ideas, established, and then the take-home exam will be, can you put the ideas together to solve something else? So if you look at those problems and you're like, well, wait a minute, he never did anything like that, I know. That's the point. Okay, the point is, can you demonstrate problem-solving ability? Because we all want to be what? Engineers, computer scientists, right? It's all about problem-solving. It's not about monkey see, monkey do, copy whatever someone else did. Oh, that's exactly like that. Let me do it that way. It's about looking at something, putting the ideas together, and then coming up with the best solution, right? Okay. So your first take-home exam I have here, it's due a week from today. All right. I'll hand that out later, maybe when we're halfway through. And these exams, I believe, should we look at the syllabus, or do you want to look at it, or do you want to see the weights of things now, or you want to? Okay. I don't mind doing it. It's just signing into the system wirelessly sometimes gives me a problem. I thought that was going to be the Spurs headline right there. Okay, so this is the main page of Northwest Vista, right? You log in, you put in your username and password, and if you don't know what yours is, you can come down here and you get some information on that here. Log in. You should have a tab up here. It says My Courses. Click on that. You should see Cal 3 somewhere in there. and this is our main page. Okay, so I have the little video for you to watch. I have the syllabus. I have the schedule. The schedule is what I handed you. Shows you what we're going to do. And then the class videos, everything that I'm doing right now, right? This video is being recorded. When you click on that, it'll take you to YouTube, and that's where the videos will be. All right? And then class files, everything that I write down will be saved as a PDF, and then you can bring that up and print it. So that's where everything is. So the syllabus, let's see if there's anything important here. Oh, office hours. I am available to you, office hours. You can walk in and get help. I plan on being here, an hour and a half before our class. And then after our class, I'm leaving. But if it turns out that more people want me here after class than before class, I'll adjust as we go. But that's just an opportunity for you to come in and get help. Now, maybe your whole life through calculus you've never needed help and you're fine on your own. That's great. But if you need help on these take-home exams, which I expect my students to need help, all right, then your one point of contact is me. You know, I want to get to know you. I want to know your abilities. I want you to bounce your ideas off me. This is a time when we can meet to talk about that, all right? And then Tuesday, Thursday, I'm also here from 12:30 to 2 in my office. Yes? In the lab, nobody does that. Well, there are some in the labs, but you're not allowed to get help on the take-homes with that. Yeah. So they already know, like I provide them my take-homes and I say don't help anyone on these problems. And so, but as far as like homework problems out of the book, there's usually, you know, 1 or 2 tutors in there that can help you. But my opinion is just that anyone tutoring you in Cal 3 should probably have a degree in math at that point. So not just, oh, I passed Cal 3 or, you know, even I got an A in Cal 3. You want someone who's beyond a degree in the field before you start getting help, so they can maybe explain things a little better. So we're kind of at our limits at this college of courses that, you know, tutors, if that makes sense. The book I showed you, here it is. There's the ISBN. I said in my video, I think I said also, you can have like an iPad if you want to take your notes on that, or if you have a tablet like I do and you want to write your notes or something, you're free to do that. Okay, just let me know. That way I know you're taking notes instead of just surfing the web in here. The grading scheme in this class is really probably something you've never experienced in a class before. Because so much of the work I want you to do is take home, I have like a big asterisk next to the grading policy. Your final exam, okay, let me tell you why I do this. I had a history of students in Cal 2 and Cal 3 where they would do real well. They get to the point of the final and they'd realize, hey, I only need like a 40 on the final to pass the class. So they would shoot for like a 60, you know? And so they would take the foot off the pedal there at the end, and they would miss a lot of the most important information because they would just kind of not care. And maybe not care, but they would utilize their time for other classes or something. So in this class, you must do decent on the final in order for everything to work out this way. So you have to get a 50 on the final or higher in order for the quizzes I give you to be 5%, the take-homes, all of them together, 40% of your grade. So that's almost half your grade is take-home. And then you have one midterm and one final. So in this class, we're going to have a midterm final. That's it. That's the only thing you're going to have to do is sit down, paper, pencil in front of me. All right? That's the way the grading scheme will be if you can get a 50 on the final. If you do not do well on the final, then everything changes. Everything you did at home now doesn't mean much to me because I don't even know if that was you, right? You've come in here and you bombed the final. I don't even know if you know this stuff anymore. So it changes, and now if you do the math on this, it's nearly impossible to pass the class if you get less than a 50 on the final. So there's pressure on the final, but I mean, if you make it to the final, usually you'll be okay, right? What's that? Nope, not part of your grade. It's expected, but it's not part of your grade. As you might suspect, the students that I have had the most success in this class are the ones who do the homework and then go and try and do the take-homes. If you just take the take-home and you just sit there and go, I'm going to try and do this without looking at the homework, you'll probably spend, 3 to 4 times the amount of time on it. Because if you would have done the homework, you would have understood all the underlying concepts first, and then do those problems. Does that make sense? Okay. So I've already talked about this, what I'm going to be doing in class, the videos. I don't want to see you texting in class and, updating your whatever's popular nowadays, Instagram. I don't even know what. But if you're doing stuff like that and you're not doing class work, paying attention, it's a 10% penalty. It's a pretty hefty penalty on your midterms. So the midterms are next exam. If you're in here and you're like texting your friend or something, then I'll just say, hey, 10 points off. And all right, that clear? I know some people don't like that policy because, you're paying to be here, you're an adult, blah, 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 blah. But I still have control of the classroom. The state has not taken that away from me yet. So these are my rules, and we'll all be okay, right? Sleeping, same thing, okay? This isn't a huge auditorium where you can just kind of disappear behind your books or something. I mean, here I'll know if you're sleeping. If you're that tired, just don't even come into class. Go sleep on the bench out there. Just stay at home. Take an absence. Scholastic dishonesty. This is a big deal because the take-homes, right? I mean, as much as I tell people don't work together, it's natural to meet someone in class and start bouncing ideas off each other about the take-home. That's not allowed. There's only one place you can ever talk about the take-homes with other students, and that's in my office with me there. Then, I mean, if 8 of you show up and sit, we've got these big tables outside our offices where you can just sit there and study. If you show up with, a group of you show up and you want to start talking about the exam together, you can do it there. As long as I'm there to kind of see and hear what's going on, that's okay. That makes sense? But if I'm walking around, I go to get a drink over there and I see y'all in the tutoring lab or something, you're sitting there and you're all working, someone's up on a whiteboard doing a take-home exam problem, that's scholastic dishonesty. Understood? Okay. Tutoring, yeah, we already talked about that. SOBI. This SOBI statement I have to have in here. This actually has to do with like all the, I don't know exactly what it has to do with. I think it has to do with behavior of students and just people in general and how crazy this frickin' world is these days, right? So, if you notice your classmate's got his backpack there and you see a couple of magazines sitting out there, fully loaded magazines and a couple of handguns sitting in their bag, you probably want to say something, right? You know what I'm saying? You see something weird, just talk to someone about it. I also always like to try and think about an escape route if we have to. And believe it or not, even though we're on the 3rd floor, there is an awning over here. So we couldn't go out this window, but that window right there, it's about a, 15, 12-foot drop. And then from there you can run down and then you could drop again. I mean, it's not a death fall. So if we have an active shooter in the hallway and, just FYI, we know that's one way out, right? So someone over there, throw your table through the window, or we'll throw you through the whatever comes first, right? We're headed that way. I heard something one time is like, luck is prepared, what is it? Does anyone know what I'm talking about? Luck is preparation meets opportunity. That's what it is, something like that, right? So in some way we have to be prepared for an opportunity if we have to get our asses out of here. So that's where I'm going. All right, this is our schedule. And then the rest is stuff the college tells me I have to have in there. Any questions? Yes. Pardon? Oh, quizzes. Quizzes can come in any form. I mean, it can be beginning of class. I'll give you a quiz. I might make it a group table quiz. I don't do a lot of quizzes in here because we have a lot of material to cover. I mean, we're covering chapter 10, 11, 12, and 13 completely without, I think we might skip one section in there. And so if we can get to the end of the book, that's the goal, and I don't want quizzes to take up too much of that time. Now, we might have to because 3.5 hours, I need to get you, we might do jumping jacks or something halfway through or something, wake us up. We will take a break. About halfway, we will take 5-10 minute break just so you can get up and walk around. We won't go 3.5 straight. But the quizzes, if I feel like students aren't doing homework, I'll start giving quizzes on homework. And I'll pick a problem out of the homework, and that'll be the first problem, and you just one problem quiz, boom, turn it in. If you did your homework, you've seen it, you probably know how to do it. Everything's good, right? All right, let's get out of this. All right, so I use Microsoft OneNote to take the notes. And let me just, boy, I'm hitting like a shortcut key or something there every time I do that. Doesn't like my finger anymore. Has anybody ever used the math program called Mathematica? Mathematica? No? Have any of you ever used Wolfram Alpha? Oh, yeah. Right, of course. Right. Anyone not ever used Wolfram Alpha? Okay, it's time to discover Wolfram Alpha. Now, I didn't have Wolfram Alpha when I was a student, so it is possible to do all this without Wolfram Alpha. But Wolfram Alpha, as most of you know, is a very powerful website. Well, the engine, the brains of Wolfram Alpha actually come from a program called Mathematica. And so Mathematica is what I use, Wolfram Mathematica. I've been using it since I think it was version 4.1 is the first time I ever used it, back when I was a student. And I've been coding in it. It's like C++. Anyone computer science people here? C++. All my code, everything that I do, that I put up here, is the result of some code that I created. So if you're interested in any of this code, anyone who might be interested in Mathematica, I have no problem sharing all of my code, all right? But you have to come to me if you're interested in that. So what we're looking at here is actually more powerful than Wolfram Alpha in the sense that Wolfram Alpha has some limitations, all right? If you go to Wolfram Alpha and you ask it to do 3D plotting, three-dimensional, it will do it, but it doesn't have as many bells and whistles as Mathematica does. And you'll see that as we move on, the things that I can and can't do. So this will be the primary program that I use. All right, all of the little things you see here are interactive. So I have little sliders. I can adjust things. As I do this, I'll switch back and forth to OneNote, and I'll write my notes here. And we'll go back to the document and back and forth. Okay? All right, I'm ready to go. I'm ready to do this. I've been itching to get started here. So how many of you enjoyed Cal 2? Anyone like Cal 2? Yeah. Did everyone get to see sequences in series? Yes? Okay. Sequences in series were, depending on what you saw, they were, was everyone over in 309? I guess I should have put a note on the door, huh? All right, y'all come on in. Here, if y'all just came in, come grab one of these out of here. Sit. So Cal 2, how many of you have heard Cal 3 is easier than Cal 2? Anyone heard that? I've heard that too. My Cal 3 students said the same thing. It depends on you, I think. Everyone get one of those? Yes. Mm-hmm. Oh. I'll have them next. Well, you know what? Here. Take it. Yeah, sure. Okay, so yeah, Cal 3 might be easier than Cal 2. It just depends. Here's the biggest challenge, at least when I was a student, the biggest challenge in Cal 3 was the fact that we're working in three-dimensional space most of the time. All right, so because of that, and sometimes we're working in four space, meaning we have this fourth dimension instead of just the three dimensions that we are comfortable with physically. So because we're in three space most of the time, in a traditional lecture with the chalkboard and, you know, auditorium full of students, your instructor needs to be really good at drawing three-dimensionally, and you've got to be really, you've got to get good at that also, you know, and get comfortable with putting three dimensions on a flat piece of paper. The advantages with using technology is the fact that we can see all that stuff easily. We can spin it around and rotate, zoom in, zoom out. And so we aren't going to get bogged down as much as maybe I would have as a student, get bogged down into the visualization. Does that make sense? So in that aspect, in that respect, I think that Cal 3 can be easier as long as the visualization is made easy for you. So we're going to start out. We'll talk more. I'm going to, you know, kind of get back to, you know, the things in Cal 2 compared to things in Cal 3. But Cal 3 is pretty much independent of Cal 2. I mean, there are some things you need to know. You need to know how to integrate. You need to know how to differentiate. You do need to know some series stuff, but you need to know stuff that goes back to college algebra too. So I mean, it's all built in, but idea-wise, a lot of it's new. All right. So we're going to start. Our first note here is points in R1. So what does this little R1 up here mean? First dimension, like a line, right? R1. So a little superscript up there, exponent thing. 1 just lets you know. If I just wrote R by itself, that double struck R, that would mean R1. So we know that if I say X is negative 1.43, and we are in R1, we're talking about a point that lies on a line, X value meaning left of 0, 1.43, right? I mean, this is about as basic as it gets, right? Everyone agree? Move it around. That's fun, right? Okay, now we go to R2. Once we're in R2, now we have what's called an ordered pair, right? A point in R2 has an X and a Y coordinate. Agreed? Move the X around. You move left, right, move the Y, change the Y, you go up, down. Now, why do they call it an ordered pair and not just a pair? If I say 1, 2, is that the same as 2, 1? The same two numbers, right? 1 and 2, but the order matters, right? So when you say 1, 2, that means the X is 1, the Y is 2. So ordered pair means that the order matters here. All right, now, when we were in R1 and I said X is 1, what was that? When we're in R1 and I said X is 1, I may not get to exactly 1 unless I do this. Oh, what the hell's wrong with that thing? That's going to really start to piss me off. Are we happy if I just leave it like that? If X is 1 and we are in R1, what are we looking at? A point, right? A point. A point on the line, right? Now, if I go to, let me make sure I'm still recording here. Yes, I am. If I go to two-dimensional space and I say X is 1, what is it? It's a line, right? It's not a point anymore. So if I say X is 1, right? That's what it looks like, this line. And so what we look at is by saying X is 1 in R2, you're saying the X coordinate is 1, but your Y is free to be anything at once. So you could have 1, 0. You could have, all right, 1, 0 would be down here. 1, 1 would be up here, right? 1, 2 would be up here. So the vertical line there, the Y coordinate is free. Now, we could also do an equation something like Y equals a constant. So if I do that, I get another line, but this time it's horizontal. and your x variable is then considered to be free. Is anyone here taking linear algebra? No linear algebras yet? Okay. See the difference? What space you're in dictates what you're looking at. So if you just say the answer, you know, x is 2, it's not necessarily a point on the line unless you know what space you're in. Okay, some other common lines from R2 that we've seen. Y equals x is, what do we call this? Y equals x? It's has a special name. It is a parent function, and it has a specific name to it. Anyone? Identity. It's the identity function. It's the identity, right? What goes in comes out. You plug in 2, it spits out 2. You plug in 3, it spits out 3. So identity, identical input and output. And then you have, okay, well, if you change the number in front of the x, then its slope is different, right? You get the line steeper, or you know, if you put a negative in front of it, then you get a negative slope, right? Okay, now let's talk about 3-space. In 3-space, you're now going to have a third dimension. So you have your flat piece of paper. Here's our flat piece of paper we've always been dealing with, right? Here's our x out the right side. Here's our y going up and down. So x is the measurement from here to here, and y is the measurement from here to here. Now that we're in R3, what we're going to have is a third axis that comes out of the page, right? And this is going to be our z-axis. So in order to be somewhere in 3-dimensional space, you not only need to know an x, you also need to know a y, and you also need to know z, right? To get you where you are, wherever you need to be. So instead of calling it an ordered pair, we call it what? What do you think? Do you think order still matters? Yeah, so ordered what? Triple. Trio, yeah, triple's what we use, but you got the idea. So it's an ordered triple. When you have an ordered triple, you have 3 numbers, 1, 2, 3 right there. And that's your x, your y, and your z. So what I'm going to do now is I'm going to pop this thing out of 2 dimensions into 3 right now. So here it comes. So there's my third dimension. Do y'all see it? So that's still the ground that we had before, but now that's our z-axis. Now notice to the right, these are x values that are positive, right? And then this way is y values are positive, and then this way z values are positive. And we're going to talk a little bit more about that. It's called the right-hand rule, and let me get to it. But let's just move things around here. Our x value, I can change my x value. That puts me over here. That makes sense that it would be there. Move my y, puts me over here. Let's see, if I take my z and give some z value, takes me up, and then I can go down, right? Now, what would x equals 1 be here? Plain. So what you're allowed to have is your x has to always be 1, right? Your first coordinate always has to be 1, but your y is free, which we knew in 2 dimensions drew a line, but then also your z is free, so it draws a line. And so what you get are all the combinations of all those lines, and so you get a plane. So here's what it would look like. And let me move to x equals 1. .95, close enough, right? So can you see that plane there? Y'all see that? So if you go to that plane, notice that if you pick any point on this plane, the x coordinate is 1. All the other things don't matter. Now, what would y equals a constant be? Oh, let's talk a little bit about this a little bit more. What if I move this to x equals 0? X equals 0. This plane that I have here actually contains 2 of the axes. Which axes are part of that plane? The y-axis is in that plane, right? And the z-axis is in that plane. So we call that the yz plane, all right? The yz plane is the plane that you get when x is 0. Got it? What about if I fix my y to be a number and let the other ones be free? Then I get another plane. Do y'all see that one? And now if I move that one to 0, so if y is 0, what two axes are part of this plane? The x and z, so we call that the xz plane. And then finally, if I let z be 0, right, I get this like flat, it's like the roof of this room, right? If I move it down to 0, we call that the what? The xy plane, because it contains the ground, right? The x and the y plane, or the x and the y axes are contained in that plane. So it's the xy plane. So x equals 0 is the yz plane, right? Y equals 0 is the xz plane, z equals 0 is the xy plane. Questions? The right-hand rule. Okay, the right-hand rule set, is that in your notes? Yes, okay, good. There may be typos in the notes, okay? I don't claim to have these like published. These are just my notes I've decided to share with you. All right? So if they have mistakes, oh well, we'll be all right. So the right-hand rule says this: if you take your right hand, oh well, I should say it this way. Before I get into that, let me show you something. Where's my? There it is. Show you something real quick. If we go to R2, okay, the standard convention that we use when we draw R2 is to always have the, do we have enough space? There's some space up here. I don't know if you want to be that close, but the standard convention that we use when we draw R2 is the x-axis, the positive direction's to the right, and the y-axis, the positive is up, right? Would it be incorrect if I decided to draw R2 this way? Well, the way it works in math is, imagine if I'm looking at R2, now I can't show you this in a video, but I can just stand here. If I'm looking at R2 like this, got x positive this way, y positive this way, right? Okay, but what if I'm in the other room, right? If I'm in the other room looking at it, so I'm on the other side of this looking at it, what does it look like? It looks like this one, right? So it's just a matter of orientation, where you are. If I turn things and flip them over, I can make the blue one become the black one, and vice versa, right? And it turns out that with R2, it does not matter how you label your axes. All the math stays the same, okay? Doesn't matter. But in R3, it does. Okay, so let me show you an example in R3. If I draw, now how do you draw a three-dimensional space in R3? There's so many different ways of doing it. Here's one way. You can draw a line, that's your z-axis. And then you can do like a squashed down looking, ooh, boy, I missed it. A squashed down looking X. So it's not a perfect, they don't hit at a 90-degree angle. Do you see that? These two don't hit it on 90. I've squashed it down. If you do that, that's a pretty good representation of three-dimensional space. A lot of times physics, you'll draw it like that. Have you all seen that before? Okay, but we have to pick which axis is x, which is y, which is z, and what is the positive direction. So if I pick, let's say this is x positive, this is y positive, and this is z positive. That's what I showed you when we were looking at the point moving around the planes. That's the way I drew it. Then, would it be okay for me to write this? Would this be the same thing? X, or y, x, and z here. Well, without us getting into too much detail, there's no way that I can move around, get on the other side of this, flip it, rotate it, and ever get it to look like this. It's impossible, right? So I can't just transform this with movements, and get the one on the left to look like the one on the right. Does that kind of make sense? So what we have to do is we have to agree, we all have to agree, how we're going to draw 3D. And the rule that someone came up with is called the right-hand rule. I guess because most people are right-handed, they said, well, people won't forget you're right-handed. So you take your right hand, and the way it works is that as you're looking at your three axes, your thumb always should point in the positive Z direction. And then your fingers, as you curl them, they should start pointing down the x-axis. When you curl them, x positive. When you curl them, they should go towards the y positive. Thumb always pointing Z positive, right-hand rule. So going back to my picture here, is this one right-hand rule? Yes, because if my thumb's pointing to Z positive, right, my fingers are going down X positive. As I curl my fingers, it goes towards Z positive, doesn't it? Y positive, thank you. Do y'all see that? But over here, is it? No, if my thumb is pointed Z positive, I'm curling my fingers. I go from Y positive to X positive, and that's not right-hand rule. It's got to go from X positive to Y positive. So that's our standard convention, the right-hand rule. Okay, now just like in two-dimensional space, right, in 2D, when maybe you took like a pre-cal class or something, they said, hey, when you're in 2D, you have 1, 2, 3, 4 quadrants, right? And why did they number them that way? Why did it go one counterclockwise like that? Just to confuse you, right? Why didn't they just go like top left 1, then 2, then 3, then 4? Come on, there's a reason. It might be so. Yeah, what is the standard angle? Where does the standard angle in pre-cal always start? Pointing out the x-axis to the right, correct? And then a positive angle, right, starts to go counterclockwise, doesn't it? And so as you go and the angle gets bigger and bigger and bigger, you go this way, right? So it would make sense that you want your quadrants, you want to go through your quadrants in order, right? You want to go 1, and then you want to go to 2, and then you want to go to 3, and then you want to come back to 4, right? It would be weird if you went from started in 2, then to 1, and then to 3, and then, right? You'd skip around. So that's the reason why they're numbered that way. Well, that's in 2 space. In 3 space, we actually have octants, right? Octants instead of quadrants. See, in pre-cal, any angle that lived in here, right? If your angle, let's say theta, was between 0 and pi over 2, you were in quadrant 1, weren't you? I got to get my writing back in order here. Haven't been writing in about 5 weeks. Okay, that's what it meant to be in quadrant 1, right? And then quadrant 2, you were between what and what? Let's see if we know our angles. Pi abs to pi, and then pi to 3 pi over 2, and then 3 pi over 2 to 2 pi, right? So those are your 4. Well, over here in octants, it's kind of weird to talk about an angle, because think of me pointing out the x-axis here. The angle, if I point somewhere, I actually would need to have 2 angles, wouldn't I? Like imagine I'm standing here at the origin, and I want to get to the projector, right? I have some angle, right? It's not just, I can't just sweep one way and get to it. You have a question?
Yeah, for the octave,
Mm-hmm.
that's something going to be like for a math class, right? I mean, I think static, if we did vectors, and we never talked about octave.
The only reason we're talking about octants is just to get us comfortable with 3 space and just comfortable with the regions of 3 space. And so I guess to answer your question, maybe, I don't know, it might come up in some other engineering application. In fact, there are some engineering applications where you're having to do like inverse trig functions, and you restrict your inverse trig function to certain angles. Well, there are some that are 3-dimensional trig functions, where if you want to do inverses, then you need to restrict it down to certain octants. So it's just definition, really. So if we're in the first octant, okay, if we're in the first octant, then that means the analogy here would be if I'm in the first quadrant, both my x and my y are both positive, aren't they? X and y are both positive. So let's take that same idea into here. To be in the first octant, my x, my y, and my z are all positive. That means I can be any point in this infinite cube that keeps getting bigger and bigger, right? Any point that lives in that cube would be regarded as a point in the first octant, wouldn't it? That make sense? And then the second octant, you have the x coordinate. I'll put that in here. So first octant, x is positive, y is positive, z is positive. The second octant, the only thing that changes is that your x is negative this time and your y and z are positive. So that gives you everything in that blue infinite cube. It keeps going forever, right? And then you have a third octant. Where do you think the third octant is? So I had x positive, y positive, z positive. That was this one. I had x negative, y positive, z positive. That was here. Now what do you think I'm going to get? X negative, y negative, z positive. So that should give me back here, shouldn't it? Back there somewhere. So let me pop that one in there. It should, there it is. Okay. And then the fourth octant is that one right there. And there's the information on what, what's positive, negative here. All of those first four octants were all above the what plane? The XY plane, right? Z equals 0. The first four octants are above the XY plane. The other four are below. So the only thing that's going to change for the next four is all our Z's are going to be negative, and these will rotate through the same, cycle through the same thing. So octant 1, 2, 3, 4, and then right below it, 5, 6, 7, 8. So here's 5, there's 6, 7's along the back side. Can't see it unless we spin it around. And then it's like a Rubik's Cube almost. There we go, right? Can I get rid of all that? Are y'all okay with this? Can I move on? Okay. I'll put this up here, all the information. I'll pop these out just so at least it'll be captured by the video. Those are the conditions. All right. Examples of surfaces. Okay, surfaces in 3 space. Some examples. We've already talked about some. X is equal to a number, right? X is equal to a number is this plane right here. Now I want you to see something. If I do this, if I'm saying this is X equals a number, what axis is this one right here? Right here. The y-axis, right? Notice how I was moving that. All right? That's it. Here, x is negative, isn't it? Look at that, -2. And I'm back here. So if I look at it from the side here, you see x is -2 there? That means this axis is my x-axis, right? This one is my y, and this one is my z. Let me pop that one out of here. Get it off. Oh, get it back there. Okay, and then we already said if y is a number, right? It's this plane. And then if z is a number. So let's take a look at that one right there. That's z equals 1.25. This plane is parallel to what plane? The xy plane, right? Parallel to the xy plane. It is not the xy plane, but it is parallel to it, meaning it doesn't intersect it. Yes? And y equals a number is parallel to what plane? The xz plane. And then x equals a number is parallel to the yz plane. All right. So those are just some examples of surfaces. Planes are surfaces. They're not the only ones, but they're examples. All right, now we get to our first equation formula. The distance between 2 points in 3-dimensional space. So if you have 2 points, and they each have to be ordered triples, x, y, z, r, s, t, the distance between them, which would be this blue line right here, that line segment, the distance between those 2 points is the square root of x minus r squared plus y minus s squared plus z minus t squared. Are we happy with just I provide you the formula, or do we want to talk about where it comes from? Yeah, let's talk about it. Okay, so let's first establish from this picture that this is x positive, right? This is y positive, and this is z positive. In order to know the distance between these 2 points, I could draw a right triangle. You see that right triangle there? And if I know this side and this side, I know the length, don't I? Pythagorean identity, right? A squared plus b squared is c squared. So what I'm going to do in order to try and figure out what these sides are is let's talk about this one first. Can you tell me what this distance is from here to here? Can you all tell by just looking at it? I'm going to rotate it a little bit. How are you getting 8? Well, don't tell me in terms of numbers. Tell me in terms of coordinates. Like, because all we know is it's x, y, z, and RST. Z minus t. Why is it z minus t? Well, isn't it just however high this point is, right? Up and down? This point's third coordinate, right? Its z value. And then this one has its own z value. So the difference between those should be this height, shouldn't it? The difference between the z coordinates should give you this height. So what are the third coordinates? It's z and t, right? So take their difference, and that's that height. That makes sense? But this one is not so easy. This one right here. So for this one, let's look at it from the top, like this. Do you all see that? Now, what if I drew another triangle that went like this, and this another right triangle, like that? What would this distance? So I can't draw on top of that, unfortunately, but here to here. What would this distance be? What axis was this? It was the x, right? Wouldn't this be the difference in the x coordinates? And then what would this be? The difference in the y coordinates. And therefore, this would be the distance between those 2 points, which would be this distance squared, right, plus this distance squared, square root. So I'll leave it just as an exercise. I do offer bonuses here throughout this semester. I'll make this your first bonus, and it'll be a pretty easy one. Not because it's easy, but because you can Google it, and it's easy that way. But I encourage you to try and do it yourself. Derive that formula on your own. Don't pick points. Like, don't actually plug in 1, 2, 5. Use x, y, z, RST, okay, and use the logic I just displayed to you to see if you can derive that formula yourself. Do next class. Beginning of class. If you want, it's a bonus, all right? But if not, if you don't feel like deriving it, we'll just take this formula on faith, and that's it. Now, another equation that we should be familiar with, it's going to come up a lot in this class, is very similar to something you saw back, I don't know, before today. If you have in two-dimensional space a circle centered at a point, let's call it HK, with a radius of R, then the equation of that circle is what? X minus 8 squared plus y minus k squared equals R squared. That is the general equation of a circle centered at HK, radius R. But now we're in 3 space. So instead of having a circle, we are going to have a sphere, right? We will try and use sphere to mean the shell, all right, as opposed to a ball, which would mean we include everything inside of it also, all right? Now, when you think about the definition of a circle, the definition of a circle is all of the points that are equidistant from some point. So if you take a point in two-dimensional space, boom, here it is, right? and you look at all the points that are distance r from it, you draw a circle. In 3D, you take a point. This time we can't say HK, we have to say H, we have to say K, and we have to say L, right? HKL, that's our center, and then take all the points equal distant from that. So now you draw a circle, but then you can spin it around this way and every direction, right? And so you create the shell. And the equation of that sphere is this. X minus h squared plus y minus k squared. That's exactly the same as circle in 2D. Now we have this third piece, z minus l squared equals r squared. Course radius gets bigger. Ooh, right? All right, here's a coconut problem. So we've seen coconut before, right? Coconuts are not perfect spheres, but we'll just say they are. Say you have a coconut, it's a perfect sphere. Where was it? There was a culture. Was it the Chinese that you weren't allowed to try and draw a sphere? They would execute you. Have y'all ever heard that before? If you not modern day, well, maybe modern day, I don't know. But I read somewhere a long time ago that in ancient days, the Chinese, if you tried to draw a sphere, they would execute you because they considered the sphere to be perfect. And so if you were trying to replicate perfection, it was worthy of death. I don't know. So let's imagine this is a perfect sphere, and inside of it, and actually it's a ball, okay? And inside of it, we've taken some of the inside out. And that inside that we took out is also a perfect ball. The question would be, how could I describe to you, let's say, I'm trying to make that run through the XY plane. So imagine I take this coconut, this perfect coconut that's a little hollow on the inside, and I slice the bottom half of it off, okay? And let's look at the outside radius. It looks like, although it's hard to see, let me zoom in here a little bit. Looks like we've got the inside circle. Boy, that's real hard for you to see. 5 here, 6, 7, 8. Yeah, it looks like 8. So if I were going to ask you now, look, describe to me every point that lies in this coconut. Give me a mathematical statement that describes this coconut. Well, let me help you a little bit. Could you say the point 6, 0, 0 lives there? Yes? Could you say 7, 0, 0 lives there? Could you say negative 6, 0, 0, 0 lives there? Okay, describe to me all the points that live there. But not in words. Don't tell me it's a coconut and you cut it. In mathematical terms, how can we describe it? Understand? Does everyone agree that x has to be between 5 and 8? Or are you saying negative 5 and negative 8? What about, let me turn this thing up here a little bit like this. Look at it from the side. Here's 5 and 8, right? What if I come up to that point right there? See, my x isn't between 5 and 8. I mean, you're on the right track. You're thinking through this, right? But we need a way of trying to describe it with a simple statement. Okay, good. You're thinking in the right terms now. You're saying you want all the area, or let's say volume instead, because area is like flat. Okay, volume is solid. So you're saying it's all the stuff in between the sphere radius 5 and sphere radius 8. Do y'all agree? Okay. Before we get to the answer, let's look at in 2D. It might be easier in 2D. Let's say this was 8. Let's say this was 5. Those are perfect circles, okay? And we want everything in here. So this is like a washer, isn't it? Don't get all crazy. Cal 2, we did washers. That's not what this is just a washer, okay? It's just sitting there. Did y'all do the washer method for volumes, solids of revolution? Okay. So 5 and 8. How would you describe to me that every point that lives in that area, that washer? Well, tell me about this circle here. That has circle radius 5, right? Circle here has radius 8. Do you agree with this equation? Does every point, does every x and y that satisfies that equation, does it live in that washer? This is a circle radius what? 5. Isn't that the inside of this right here? Okay. Are all those points on that washer? If we're assuming we're including the edge, right? Then those points do live on it. How about these points? Does every point, does every x and y that you can ever come up with that satisfy this equation live on that washer? Yes, right? That's the outer edge. How do I say everything between? Which is using inequality. I need my points, I need my x's, my x squared plus y squared. I need them to satisfy this inequality. It always has to be greater than or equal to 25, less than or equal to 64. And that's it. Right? This equals here gives me the boundary, and then anything bigger, right? And then this restricts me smaller than that radius of 8. Do y'all see this is just a simple inequality that describes that region? Y'all follow that? Okay. So let's get to the coconut problem. What's the only difference? Yeah, we just add a plus z squared because remember, the equation of a sphere is this, right? Here, if our coconut's at the origin, which we're assuming, right? Then I have h, k, and l are all 0. So it becomes x squared plus y squared plus z squared. That has to be greater than or equal to 25, less than or equal to 64. So the coconut problem would be this. 25 less than or equal to x squared plus y squared plus z squared less than or equal to 64. If you want to look at it more generally, forgot to square those. This would be a coconut that's trapped between two arbitrary radii, right? Radius 1 and radius 2. Assuming radius 1 is less than radius 2. That would be your inequalities. I guess all I'm trying to get across with the coconut problem is just that there are ways of describing solid figures very simply if you can use certain equations that you know. Questions? Okay, I believe that that's the end of this section, right? All right, so it's 2 o'clock. We go till when? When did we start? We start at 1. So we're going to go probably another half hour, 40 minutes before we take our first break. Right? Is that all right? Yeah, somewhere around there. So far, Cal 3 is easier than Cal 2? So far? Okay, vectors. Vectors are very general things, okay? When you're in physics and you're in math, we usually, at this level, all have the same idea of what a vector is. But are there any math majors? Any math majors? Okay. If you're a math major, you'll learn later that vectors can be things that aren't even like what you would think of, an arrow like pointing out, you know, a vector can be a function. So we focus on just the idea that most people are comfortable with, but later on it might become something else, just FYI. So vectors are objects that have two main properties. They have a magnitude and they have a direction. A magnitude and direction. That's it. We call the magnitude, sometimes we call it the length, sometimes we call it the norm, and the direction is the way it points. In two-dimensional space, a vector just looks like an arrow, right? You have the tip is the arrow which way it's pointing, the tail is this side, okay? And I can move that thing around wherever I want. As I move it around, its length changes, right? Its norm. Right? So that's the idea of a vector right there. That's in 2D. In 3D, same thing. Now, I can't grab those and change them around. That's actually a limitation of Mathematica. I can't do that yet. Maybe another version. But you can see it lives in three-dimensional space, right? It has a direction and it has a length. Now we have some terminology here. The tip of the vector we call the terminal point, terminal meaning ending point, and then the tail is actually called the initial point. This V with this little half arrow on the top, it's like an arrow, but you cut off one of the sides of the arrowhead. That's the notation we use for vectors. A lot of books use a bold instead, all right? I believe our book uses bold to represent vector. I can't use bold because I can't write in bold, right? It's easier for me to draw the little arrow on top. So you'll see me using that notation instead of bold throughout the semester. So anytime you're looking at a vector and you're representing a vector, you have to have that symbol or somehow let people know you're talking about it. A vector as opposed to a line segment. A line segment connects 2 points, doesn't it? Yes? Line segment? Vectors are not line segments. This is referred to as a displacement vector. Okay, two vectors are said to be equivalent or equal if they have the same magnitude and same direction. Position does not matter. So if I look at these two vectors here, and we were to get the measuring stick out here and measure these, they have the same magnitude, same length. And they appear to be in the same direction, don't they? So they are equal, meaning there's no way to distinguish the two. The position of the vectors is irrelevant. So as I move them around, up or down, those two vectors are identical. Now, why are vectors used? I mean, like, why not just use line segments instead of vectors? Like if I draw this line segment that goes from here to here, right? That's obviously not the same length, but that line segment connects 2 points, doesn't it? And if I move it, it now connects 2 different points. And so line segments do depend on where they are, right? The points that they connect matter. With vectors, it doesn't. So why do we like to use vectors in like physics classes and stuff? I don't normally carry a rolly cart. I only did because I brought all your stuff today. I think they're kind of dumb, but... Okay, so if I'm pulling this rolly cart around like this, I can describe a force that I'm applying onto the cart, right? Onto the handle. That force would be coming like from my arm here, right? That force is pointed in this direction, has a direction, has a magnitude, how hard I'm pulling, right? And as I move, let's say I just move at a constant speed, I keep that same force applied the whole time, you can look at my arm and that force as a vector. And it's moving, right? But it's still the same force. So that's why we like vectors, because they can be moved around in space and still they're always the same. Does that kind of make sense? Gravity, another example, right? It's a vector towards the center of the Earth. Its length is the strength of the gravitational force. Okay, determining a vector from 2 points in R2. So let's say we have 2 points. So now we're talking about points, right? Not a vector, 2 points. We have x1, y1, we have x2, y2, right? Then the vector from A to B is denoted like this, A, B, and then you have that little half arrow on top. And very important here, the order of this matters. If you're going from this one A, x1 and y1, to the point x2, y2, then the vector is written with this. Anyone know what that's called right there? It's not a parenthesis. We use that specifically for vector notation. Angle bracket. Angle bracket. Okay, so angle brackets is to let everyone know we're talking about a vector. It is the x-coordinate of the second point minus the x-coordinate of the first point. And then you have the y-coordinate of the second point, y-coordinate of the first point. Now, if you go the other way around, you want to go from B to A, the order switches. All right, we use the angle brackets. Oh, it says angle brackets right there. I must have added that like last semester or something. Okay, so here we go. Let me show you. Here's 2 points. From A to B is that vector. From here to here. The other way around is that vector from here to here. Are they the same? Are the vectors, is the vector going from A to B the same as the vector going from B to A? No. Why not? Different directions, right? Same magnitude, different directions. Now, if you're in R3, right? If you're in R3, and now you have an ordered triple for a point, another ordered triple for the other point, you can define the vector from A to B the same way we did in 2D, except that now you have this third piece here, all right? And then the other direction, you just flip them around. Hold on a second. Yeah, I'll get to that in a minute. This is just an exercise. You think you could do that? Is that almost too trivial, or should we do it? I don't want to assume too much, but I don't want to insult anyone either. Let's just do this. This is our first day. Let's just do this problem, all right? Let's see how I can. Oh, you know what? I'll break out my notes. You go ahead and get started, and I'll catch up with you here. There we go. So A is the point 6, negative 5, 6. B is the point negative 2, 8, 10. And I'd like us, for the first part of this, to find the vector AB. Angle bracket, angle bracket. So what do you do if you want to go from A to B? Is it x1 minus x2? Well, it depends on how you label these. If this is x1, y1, z1, and this one is x2, y2, z2, then if I want to go from A to B, I actually do x2 minus x1, and then y2 minus y1, and then z2 minus z1. If you do it the other way around, it'll be incorrect. So you're taking the points, the coordinates of the second point, subtracting the ones from the first. So what will we get here? We have negative 2, we're taking away 6. Then we have 8, we're taking away negative 5. Then we have 10, and we're taking away 6. So this gives us the vector, yes? Negative 8, 13, 4. Agreed? Okay. Now, if we want to go the other way, you're just going to switch the signs, right? And you can check it with the math, but if you do it the other way around, you get everything the opposite. Is that all right? That's our first example. All right, now there's an important vector, two important vectors that I put them in bold just to really stress that they are vectors. But the 0 with the little half arrow on top of it, the vector symbol on top, is not the number 0. Okay? The 0 is the 0 vector. And therefore, if you're in two-dimensional space, your 0 vector is actually this angle bracket 0, 0. And if you're in three-dimensional space, the 0 vector is 0, 0, 0. The order triple, 0, 0, 0, and it's an angle bracket. Now, both of those vectors don't have any magnitude, right? Magnitude of 0. But just know that the 0 vector exists. Now, here's some more terminology. If you're given the vector v, where v1 and v2, right, are these two numbers that usually, then we say that this vector has two components, v1 and v2. We refer to v1 as the x component, not coordinate, okay? Coordinate is what we use for ordered pairs, points, right? Ordered pairs, we say, oh, the coordinate, the x coordinate is this. The y coordinate is this. If we're talking about vectors, we say x component, y component. Two different words, all right? Now, if we're in 3D, now our vector has three components, and they're referred to as the x, the y, and the z, respectively. Now, we're going to look at a very important property of vectors called the parallelogram law. When we add two vectors together in R2 or in R3, the way we do it is to take the tail of one vector and paste it to the tip of the other. You've probably heard tail to tip, tip to tail, or something like that, when you're adding two vectors together. Either way, the resultant vector, when you add two vectors, the result, all right, is going to create this parallelogram thing. So take a look at this. I have a vector here. Here's the vector u. It's this blue one right here. Its initial point is here, and its terminal point is here. Then I have a vector v, which I'm adding to it. Now remember, v can be anywhere, can it? V is a vector. Doesn't matter where it is. If I add these two together, I have to attach the tip of u to the tail of v, and then follow the path. Start here, go up, and then back down. And what happens is, instead of going through this path here and then down, the result is just that you went from here to here, right? So u plus v is this new vector, the black one right here. With me? Now, what if I did it the other way? What if I attached there? Look. Now what I did is I took the red one, right? And I attached the tip of it to the tail of the blue. Isn't that kind of opposite of what I just did a second ago? Well, then I would follow the red, and then I would go the blue, and that's the same as going this purple, isn't it? But wasn't that purple exactly the same vector as the black one a second ago? Yes. So it turns out that it does not matter which way you go. You could go u plus v or v plus u. In either case, you would get the same resultant vector. So is it on my next slide? No, I don't have it. I'll just draw it on top of this. u plus v, which was u and then go down v, was the same as v plus u, which is that vector there. So those two vectors are the same, right? They're pointing in the same direction, have the same length. Notice if I do it either way, it draws a parallelogram, right? See my parallelogram? And that's why they call it the parallelogram law. Kind of make sense? I have to do this one on the board. I can't. I have a program that I can draw on top of this screen, but I just don't feel like using it. Sometimes it causes things to get a little unstable when I've got too many programs running at one time. So let's try this. U plus V. This is a visual problem. It's not supposed to be a perfect calculation. So what I'm going to do, U plus V, or sorry, V plus U. Here's V, right? I need to take U and I need to attach it tip to tail. So here's U. It's about that long. I need to keep this parallel. I need to move it about right here. That, right? That's U. That's V and that's U. So the resultant would be that right there. That would be V plus U. Agreed? What would U plus W be? So how about we take U again? How about moving U over and attaching tip to tail here? Is it okay to do U plus W instead of W plus U? Yes, because we just said parallelogram rule says it doesn't matter which way you go. So I'll take U again, try and keep it parallel, move it over here. Looks like I'm about here. That look pretty good? That's my U. And then attach, wow, like that. That's U plus W. Then V plus U plus W. Let's put them all together. So you do it twice. I'll let you do that yourself. All right? You would just do two together and then draw from the first one all the way to the end of the other one. Remember what I said earlier, the problems I do in class, just basic concepts, right? Homework is a little more than that. Take home, definitely this is not even in the same category as take home problem, right? You will not see anything like this. You will definitely not see something like that on a take home exam, all right? Or an in-class exam, you never get something like that. This is just the foundation. Okay. Vector addition. If you have two vectors U and V, what is this one right here called? It's the X component of U, right? That's the Y component of U, right? That's your X component of V and your Y component of V. If you want to add the two vectors together numerically by hand instead of visually, all you have to do is add the components up. It's pretty nice. If you want to subtract, now be careful here, because with subtraction, the order does matter. Remember, addition is commutative. Doesn't matter which way you go. Subtraction does. If I want to take the vector U and subtract the vector V, I take the X component of U and subtract the X component of V, and then the Y component of U and subtract the Y component of V. And then in three-dimensional vectors, it's the same thing. So pretty straight up, nothing complicated. Scalar multiplication of vectors. So if you have a vector V and a scalar C, scalar means like a real number, right? Just some real number. Then C times V changes the shape of V. If the absolute value of C is bigger than 1, it stretches it, makes it longer. If the absolute value of C is between 0 and 1, it shrinks it, makes it shorter. If C is negative, it flips the vector over, points it in the opposite direction. It can, if C is negative, it changes direction. If C is non-negative, it'll just either stretch it out or shorten it, which this visual will show you. Let's see. There's a vector V, okay? There's a vector V. It's the black one. You can't see it. And then here, the red one is 1 times V. Well, 1 times V is just V, isn't it? Now, what if I change the number in front? So now instead of putting 1 in front of V, I put 1.25 in front of V. 1.25 is bigger than 1, so it stretches it out. So the result is a longer vector. I double it, or that would be double, right? That's twice as long. Point in the same direction. If I would have made the C smaller than 1, but bigger than 0, then it shrinks it. So it's half as long now. But if I make the C negative, uh-oh, what happened there? 0, right? I got 0, 0 vector. I scaled it by 0, which gives me the 0, 0 vector. Now here are negative C values. So notice negative 1, it's the same length, pointed in the opposite direction. Okay? Questions? This is a real important definition you should remember, or property of vectors. Any two vectors are said to be parallel if they are scalar multiples of one another. Note, they could be pointed in opposite directions. Go back here. Is this black vector and this red vector, are they the same vector? Are they equal? Are they equivalent vectors? Right there as they appear, are they equivalent? No, why not? Magnitude's not the same. Direction's not the same. Both of them, right? How about if I do this? Well, that ain't gonna work. How about if I do this? Are those equivalent vectors? Same length, not same direction though. So they're not equivalent. Are these two vectors parallel? Yes. They're parallel because they're scalar multiples. It has nothing to do with the direction necessarily. The fact that they're pointed in opposite direction has nothing to do with the fact that they're parallel. The fact that they're parallel is because they're scalar multiples. Are these two parallel? Yes. That's more natural for us to think that, right? Yeah, they look pointed in the same direction. They're parallel. That's not the definition of parallel, though. Pointed in the same direction is not what it takes to be parallel when you talk about vectors. Scalar multiple is what it takes, okay? Don't forget that. It's going to come into play. All right, how do you find the magnitude or the length of a vector? Well, what we do is we have a notation for it. We use the absolute value symbol. And the definition is the length of a vector, the absolute value of the vector, is equal to the square root of the sum of the squares of the components. So it's basically your Pythagorean identity solved for one side. And then it works the same way in 3D. Ugh. That looks like busy work. Let's do example 4, okay? I think if I do example 4, example 3 will be probably pretty trivial. So let's say we have V is the vector 2, 3, -5, And let's say u is the vector -5, 7, -2. Let's do part A. V minus u. What would that be? V minus u? I'm doing 2 minus -5, right? 3 minus 7, -5 minus -2. So what would that give me? 7, -4, -3. All right, what about part B then? What's u minus v? Isn't that the same as that one, just change the signs? Right? -7, 4, 3, so I don't have to do a whole lot of work for that. How about this? What's 4v minus 3u? So the question becomes, how do you scale, right? How do you scale a vector? How do I multiply a vector times 4? Well, I just distribute the 4 through to each of the components. So I'm going to write it out so we can see it. 4 times, now the vector v was the vector 2, 3, -5. And then I have minus 3 times the vector u, which was -5, 7, -2. And now, really, it is like a distribution. The 4 goes through. And then here, you have a choice. You can pass a 3 through, a positive 3 through, and keep this as a negative sign. Or you can multiply through by a -3 and make sure you remember it's now a plus. Either way, I'll do just a positive 3. So what do we have here? 8, 12, -20. And I'm going to subtract from that -15, 21, -6. And then when you subtract it, you're going to take the 8 and subtract -15, which gives you what? 23. 23, 12 minus 21, -9, and then -20 plus 6, -14. So that's part C. Questions? Part D. How do you find the magnitude, right? That's what we're looking for now. The magnitude of that. Well, we already found what 4v minus 3u is, right? It's this right here. That was it. We just want the magnitude of that. So if you want the magnitude of that, you can get your calculator out if you need it. Somebody get the calculator. I didn't bring mine. It's the sum of the components squared, right? Sum of the square of the components. So it's 23 square root of the sum of the square of the components. 23 squared plus -9 squared plus -14 squared. And then take the square root. And we'll do a decimal approximation. Anybody have it? 20 what? 28.4? Any seconds on that? Yes? Okay. And since that is a decimal approximation, should I use an equal sign here? No, I should use the what? The drunk one, right? Yeah, kind of close to 28.4, right? That's what it means. That's a mathematical symbol, right? We know that. It's not just, it's made, whenever we put that, we are saying we are now approximating, as opposed to the equal sign, which means exactness, right? So we're approximating it to be 28.4. On a test, on a take-home test, sometimes I will say, find the decimal approximation, or I will say, find the exact answer. If I want the exact answer, I don't want the decimal approximation. For example, this is a side note here. If on a test, your answer comes out to be square root of 2, 3 square root of 2 over 7, and I ask you for the exact answer, you box that, right? If I ask you for the decimal approximation, you put it in your calculator and you get a decimal. Significant digits and all that, I'm not real big on, so, you know. But know the difference between exact and approximate. How many of you have a TI-89 or the TI-92? How long did it take you to figure out how to get it to not give you the exact versus the, you know what I'm talking about? Like if you type in 1/3 on a TI-89 or it gives you back 1/3. It doesn't give you 0.333. Have you figured out how to switch that yet? Okay. Wasn't it frustrating at first? A little bit? Okay, yeah, me too. But a lot of my students will get those and they're like, this thing is really upsetting me. All right, so, unit vectors. How are we doing on time? Let's see. We're close to a break. How much more do we have in this section? Break now? Break now? Okay. Let's see. How long should we break for? What do y'all think is a good amount of time? Max we can go is 10. So 10? You want the full 10? If you came in a little bit late or missed the very beginning, come talk to me, all right? Okay, back to business here. I just handed you the first take-home. Let me tell you a little bit about, before I talk about the take-home, the homework assignments. When I first made these notes that you are going to be handed, these things I handed out, right? When I did it using the first edition of the book. So the homework assignments that may appear in here are not correct. Understand that? So do not do the homework assignments as posted in these notes. I will provide you the homework assignments. I will either write them on the board at the end of class or I will email them to you. A lot of times I'll email them because I need to see how far we went that day, what we covered, and then at that point I know where to break the homework up and give you the assignment. So just so you don't go start doing a bunch of things that you're not supposed to do, don't follow the notes for homework assignments. Got it? Okay, now the take-home exam, which I just handed you. Let's talk about the instructions here. This is due 6/16/2014. Let me just double check that is, yes, that is next Monday at the beginning of class. If you come in 30 minutes to class, 30 minutes late to class, and hand it in, I will not accept it, all right? In fairness to every student in this class, everyone has a week to finish this. Well, less than a week now, right? And to give someone an extra half hour or an extra hour or an extra 6 hours isn't fair to any one of you, so I will not accept it late. Understood? If you can't be here, if something comes up and you're not going to be able to make it, and you know that ahead of time, then you need to scan what you have, email it to me, or take a picture of it, document it somehow to cover your butt, right? You want to be able to prove it. I'm not saying I want everyone taking pictures of their tests and sending them to me and not coming to class. I'm saying that would be like a last resort, is for you to somehow prove to me that at the time class started, you had this work done. Understand? You are to do all work on your own. That means no working in groups or with a tutor. All right? So to your question, I know it's very difficult to walk out of here, especially if you know someone in the class or you start to make friends, to be like, hey, you know, and I can't sit there and really govern that, but at your own risk, you know, at your own risk. These exams, the way I make these exams is that, like I said earlier, is to make you think outside of what the normal problems in the book are. You know, just trying to get you to problem solve. And so if you go and start Googling all these things, you're really trying to find the answer out there somewhere. Like I did that before I made it, you know, like I made sure there wasn't anything for you to find You know what I'm saying? So you're wasting your time. If you're just trying to find the shortcut, shortest, easiest way to not have to do the work, then it's not going to work out for you. All right? I hope that everyone in here has time. That is one thing this class requires, is time. Outside of this class. You cannot show up to this class for 3.5 hours, 2 days a week, spend 20 minutes on homework, and pass. These exams can take hours and hours to do. All right? They can. That's my expectation. It's 40% of your grade. It's take home, but you're going to have to work. So let's just look at this first exam to get some ideas. A plane is aimed, number one, a plane is aimed southeast. Southeast, so you got to know what southeast is. Throttle is set at 400 miles per hour. There is a 25-mile-an-hour crosswind blowing in the west direction. A person on the plane runs from the front of the plane to the back down the center aisle at 4 miles per hour. What is the speed and direction of the person who is running relative to the ground below? Now, did I give you anything like that? No. What is this problem about, though? Vector addition. Okay? This is a vector addition problem. You got to put it together, and you got to come up with the answer. Number two. If U and V are unit vectors on this regular pentagon, then find the following. Your answer should be numeric quantities. So I want to add one thing to this picture just so everyone's clear on it. On your pentagon, just add that this is a right angle right here, just so everyone is clear on it. It's kind of assumed from the picture that it is. But just put that that's 90 degrees. So I'm not going to show you anything like that in class again. You're going to have to do some thinking here and try and figure out what all these things are. Number 5, we haven't even really talked about this stuff yet, but yeah. There it is. I mean, this is the test. My suggestion to you would be, if you're stuck, you contact me, okay? I mean, I want you to reach out and get help. That's part of the design of the test, is for you to seek help. There's so many students that I meet that think that they can do engineering and math and physics or whatever it is in their little box, and that they never have to ask anyone for any guidance, that they can do it all on their own. That's not the point of this test. The test is for you to, if you're stuck, try and get around it, think through it a little bit, but don't spend 4 hours on one little thing if you could just ask me, because you will spend 4 hours on one thing if you don't. It can become very ugly. On number 3, I would like for you to add a little thing to this. You may not use a computer to solve that problem. You cannot get a computer to graphically give you an answer or a computer to numerically give you an answer. That problem can be done completely by hand without any aid of any computer. I want to see if you know how to do it. If you don't, I will show you how. I will show you the method, and I won't show you how to do that, but I will show you what method you need. Okay, let's get on to the lecture. We'll have plenty of time to talk about these mini tests. My cell phone is on the syllabus. You can text me, okay? That's fine if you text me. Just make sure you put who you are and what class you're in, Give me your name, Cal 3 or 2415. If we're texting back and forth, we'll at least start that first one with who you are, and then after that I should have the log, what I'm talking about, and I should be able to scroll back up and see who you are. So the first one, at least let me know who you are, and then we'll get some dialogue going on. And, that's one advantage to small school, 28 people is that I can actually get to know people in the class, right? As opposed to, what, 100, 200, very impersonal, right? Okay. Any questions? All right, unit vectors. So any vector with a length of 1 is called a unit vector. So what I want you to see here, this blue vector is just some blue vector, right? It has some length to it. And pointing in the same direction as that blue vector is this red vector. And that red vector has length 1, right? If I move this blue one around, it doesn't matter where I put it. There's always a red one pointing in the same direction with length 1. Always. Unless that blue vector is what? 0 vector, right? Because 0 vector doesn't have a direction. So there would never be, you couldn't have a unit vector pointing in the same direction. So with the exception of the 0 vector, for given any vector, there's always a unit vector pointed in the same direction as that one. The question becomes, how do you find it, right? How would I find that red vector, right? How would I find it? So check this out. This vector, this red vector, is a scalar multiple of the blue one, isn't it? A scalar multiple? Because it points in the same direction, correct? And its length is got to be 1. So what if this blue one had a length of 2? How could I get the red one? If that blue length was 2, how could I get this red one from it? It would just scale it by 1/2, right? Divide it by 2. Scale it by 1/2. What if the length of the blue one was 3? I would scale it by 1/3, right? To get the red one. So if the length of this vector, the blue one, is, let's say, k, then I would scale it by 1/k, or scale it by 1/k, right? So that's where this formula comes from right here. Given any vector u, it doesn't matter if it's 2D or 3D, we can always find a unit vector pointed in the same direction as that u by taking the u and dividing it by its own length. Or in other words, 1 over its length times u. So all we have to do is find the length of u and divide each of its components by that length. So let's find a unit vector in the same direction as that one. Let's see, v, I'm calling it v. So if v is pointed out in 3-dimensional space somewhere, right? And I want to find the vector that's pointed in the exact same direction, but it only has a length of 1. So what I need to do is I need to find the length of this vector. So what is its length? Square root of 4 plus 9 plus 25, which is, we'll leave it in its exact form for now. Square root 38, right? Root 38. And now what I need to do is I need to take that vector v, I need to divide it by its own length, which is the same as taking each of its components, and dividing it by root 38. And that's it. I can promise you that that vector points in the same direction as the original one, and the length of it is 1. Do you believe that its length is 1? How could you check it? How could you check to see if the length of that is 1? I could check the length of this and do the square root of each of the components squared. So square would be what? 4 over 38, because you square the 2, you square the square root, and you get this. Then this squared, which would give you what? 9 over root 38, or sorry, square root of 38 got squared. And then plus negative 5 squared, so 25 over 38. And when you add all those together, you get 38 over 38, which is 1, and square root of 1 is 1. So you get 1. So that's just to check it. That's the way it's done. Questions? Now that's not too bad, right? I mean, it's just very mechanical. Now look at this. I want you to see something. Okay, that's some arbitrary vector u, right? What is the length of u? By definition. All right, there we go. Now, what would u over itself be, or its length be? That's that u1, right, over the square root of all that, right? This stuff? Agreed? So I'm just going to do that. How about that? That's very, very lazy. u2 over what? Square root of all that stuff again. And then u3 over square root of all that stuff again. Agreed? What's the length of that? What I'm trying to do is show you why this works, or prove that it does. I took a vector u, I took its length, I took the vector u, I divided it by its own length, and now I'm going to take the length of that and show you that it's always 1. So take the magnitude of this now. The magnitude of u over the magnitude of u. And so you do square root of each of those things squared. So what would happen if I square this right here? I get u1 squared over what? Just the yellow stuff, right? Because the square root's going to get squared. So I got the yellow stuff. And then I have plus, now what? u2 squared over the yellow stuff, and then plus u3 squared over the yellow stuff. And then wouldn't you get u1 squared plus u2 squared plus u3 squared all over the yellow stuff, which is u1 squared plus u2 squared plus u3 squared. So that's just 1. Yes? u1 squared plus u2 squared plus u3 squared. Put them all together. This is square root of 1 is 1. That just shows it works, okay? All right, now, there are an infinite number of unit vectors. Any vector has length 1 as a unit vector. But there are some that are very important in math and physics. They're called the standard basis vectors. And in two-dimensional space, the standard basis vectors are the vectors I hat and j hat. Have you all ever heard that before and seen that before? Okay. I hat is the vector 1, 0. J hat is the vector 0, 1. The reason that they're so important is that, 1, they are unit vectors, and 2, every vector in two-dimensional space can be written as a linear combination of those two vectors. Here's what I mean by that. Take any vector u, okay? Take any vector, I don't care where it is, put it anywhere in two-dimensional space, all right, anywhere. Then, in order to create this vector u, I can just do some combinations of those two basis vectors, the I and the j. I could take the I vector right here, that's the vector 1, 0. I can scale it by 2.52, and that would give me this vector. Then I could take the j vector, scale it by 2.63, and that would give me this vector up here. If I add those two together, it takes me, right, tip to tail, it would take me to that one. So any vector, any black vector there, can be written as a linear combination, basically scalar multiples of those two vectors I and j. So you can basically create the entire space, two-dimensional space, with just those two vectors. There were no linear algebra people in here? No? This is later on in linear algebra, you study spaces in more general sense, and these two are called an orthonormal basis for R2. Ortho meaning perpendicular, normal meaning unit length 1, basis meaning they span the whole space. You can create all of two-dimensional space out of just those two vectors. Now in 3D, you have I hat, j hat, k hat. So you throw a k in there because you have a third component. And instead of being 1, 0, your vector is 1, 0, 0 because you need three components, 0, 1, 0, and then 0, 0, 1. So what would those look like if I drew those in 3D? So let me practice some 3D drawing here. Would this be okay, right-hand rule? Assuming that those are all the positive directions of the axes. Yes, that would be okay, right? So I hat is the vector 1, 0, 0. This could be I hat, couldn't it? If this is 1, 2, right, that vector right there, that's I hat. Points out in the x direction 1, and then doesn't have a y or a z component. J hat would look like this. Right? And then K hat, K hat, 0, 0, 1 is the one that goes straight up like this. And guess what? They call these three vectors also an orthonormal basis too, because they are orthogonal, which means perpendicular. Okay, notice that those two are perpendicular, right? These two are perpendicular, laying on the ground, and these two are perpendicular. They're all perpendicular to each other, and then they all have unit length, which makes them normal. And then they're a basis because you can create any, you can get to any vector in R3 with just combining those three vectors together. So here's an example of how you can create any vector with those, with the orthonormal, well, sorry, with those basis vectors. This is really kind of trivial, but I'll do it. It's just to show you how you deconstruct a vector. Do you agree that this vector is the same as this vector? Do you agree with that? Right? You just add all these things together. If you put these two together, you get the 2 and the 3, right? Then you throw this one in, you get that -5. But then you can look at that first vector, pull a 2 out, a scalar multiple of 2 out of that. On this one, pull a 3 out. And on this one, pull a -5 out. And now, by doing that, this one here, 1, 0, 0, that vector is what? I hat. So I. And then the other one is what? J. And then the last one is K. So what I'm doing is basically showing you, the book uses this a lot. I can't stand I hat, J hat, K hat notation. I always write my vectors in that form. So this just shows you how this is really that, okay? Or that is really this. There's all sorts of different ways to write vectors. In fact, some books write vectors this way, vertically. 2, 3, -5 to mean that. And they don't use angle brackets. They use the square brackets vertically, though. Okay? So just be prepared later on as you do more math to see any of these three variations of vectors. In this class, these two would be the only ones. The hats and then that one up there. $10.2. We're done? Yes. Good, good. How is this going for you all? Y'all all right? It's a long class. All right, finally we get to something significant, the dot product. So let me say this first before we get into the dot product. We have the idea of vectors, right? This concept of a vector. And what we've done is we've added them together, and we've subtracted them. We've seen we can subtract them. We've scaled them, which stretched them out or made them, shorter. Sometimes it pointed them in the opposite direction. So naturally, just like we did growing up, we want to see what are all the operations you can have between these things. We can add, we can subtract, we can scale, but does it make sense to multiply two vectors together? What does it mean, right? Turns out there are two types of multiplications when it comes to vectors. If I give you numbers, right? If I give you two numbers and I say, all right, everyone, back in the old days, 5 times 3, everyone. Everyone's like, oh, that's 15, right? Everyone's happy about that? There was no other type of multiplication, right? There wasn't some other weird multiplication that looked like this, some weird, crazy-looking, that's too close to a multiplication. How about I'll make up my own with the dot on top? No, I'll make a little, yeah, there we go. There's my symbol. That's my other multiplication symbol, right? There wasn't some other defined multiplication, right? We only had one multiplication. That was it. It just meant, multiplication meant repeated addition, right? That meant take 5 and add it. Take a group of 5, add it 3 times. 5, 5, and 5 and gave 15. Repeated addition is what multiplication was. So with vectors, there's actually two types of multiplication defined with vectors. One of them is called the dot product, and the other is called the cross product. So two completely different operations, two completely different results. 10.3 is dot product. 10.4 is cross product. So we will get to cross product later. Here's the first type. So if you're given two vectors, and we are trying to find what's called the dot product, or sometimes books call it the scalar product, and sometimes books call it the inner product. So given two vectors in R2, we define a new type of product between them as follows. So here's our two vectors, V1 or V and U. Then U with this dot between them, and you've got to be real careful here that everyone understands that that dot is not scalar multiplication, like a little dot. That's like almost like a bolded dot. In most books, it's like a bolded dot. If you take the dot product to two vectors, all you do is multiply their corresponding components and then add them up. So I take V1 and U1, I multiply them, then plus the V2 and U2. Add them together, that's my result. Okay? Why didn't they say, instead of doing V1, U1, why didn't they say, let's do V1 times U2 and V2 times U1 and add them up? Well, they could have, but that's not the way. This is the way you define dot product. Okay? First components multiply, second components multiply, add them together. That's the definition of dot product. Now, also notice that the answer here is a number, right? We start with two vectors, we dot them together, and we get a numerical answer. Now, this is really weird. If you look back at the history of everything you've done in math, this is the first time I think this ever happens. Look, when you multiply two numbers together, back in the old days, what did you get? A number, right? If you add two numbers, you got a number, right? If you took a function and you multiplied it times another function, you still had a function, right? Even if you integrated a function, you usually got a function, right? Or differentiated a function, you got a function. This is the first time that you ever take two things, like here, two vectors, you put them together through some operation, and it gives you something that isn't even a vector anymore, right? So it's kind of an odd operation, but that's the way it goes. Now, if we have two three-dimensional vectors, then you just do the first two components multiplied, second two components multiplied, the third components multiplied, add them all up, and again, the answer is a number. Okay? Let's see. What's this dot product? Can we do this mentally? So find u dot v. So I'm going to take, what, 2 times -3, that's -6. -3 and -3 and 4 is -12. Put that together with -6, we're at what? -18. Okay, 5 and 7 is 35, so I had -18, 35, 17. There we go. We're done. What should your next question be? Well, not this, not what are the properties, but I'll talk about them. But your question should be, yeah, what the hell is it? What's the value of that? You know, like what's the meaning of it, right? If I have two vectors sitting out there and I dot them and it gives me a number, what does that number mean, right? What value does that have for me and what I'm trying to do? We'll get to it. But first, let's talk about the properties, important properties of dot products. If you dot a vector with itself, u dot u, then it's u1 times u1, u2 times u2, u3 times u3, which is u1 squared, u2 squared, u3 squared, which is almost its length. What's the length of a vector? What's the length of a vector? If u is u1, u2, u3, what's its length? Square root of u1 squared plus u2 squared plus u3 squared, right? Isn't that what you would almost get there? If you square this, what happens? You square, and that is u dot u. So u dot u is the same as the square of its length. U dot v is v dot u. Commutative property of dot products. The order doesn't matter. Distributive property of dot product over addition. If you take two vectors and add them and then dot it with the third vector, you could actually have dotted them first, like a distribution. Dot here, add, dot there. Here's the scalar property. Scalars can move around. So you can have the c in front of the u, scale it, then dot, or you could pull the c out, dot, then scale, or you could even take that c and move it to the other vector, scale it, then dot. They all come out the same. So scalars slide around. And then, as you might suspect, 0 dotted with anything is, the 0 vector dotted with any vector is the number 0, right? The number 0. Nah. Yes or no? No. You could do V and W, okay, and then take that and dot it with the U, and then scale it by 3. Now, let's get to the meaning of it, though. What does the dot product mean? So this is dot product theorem. If theta is the angle between two vectors, u and v, then the following is true. U dot v is equal to the magnitude of u times the magnitude of v cosine of the angle between the two vectors. This is a big, big result. I can do it three-dimensionally with this stuff, and then I'll show you up there. But if I have two vectors sitting here in space, right, doesn't matter. This one's pointed this direction, this one's pointed this direction. I can slide them around and they're still the same, right? So we said. So if I slide them together like this, and I go tail to tail, okay? Tip, tip, tail to tail. I'm not adding them, okay? So not tip to tail to tail. Then there is a smallest angle between them, isn't there? Now there's also an angle that goes all the way around this way, but I'm talking about the smallest angle between them. That angle is theta. That's the relationship between the dot product and theta. It's saying that the dot product is equal to the magnitude of one of your vectors times the magnitude of the other vector times cosine of the angle in between them. Most importantly, it connects the angle to the dot product. So given two vectors, if the angle between them must be between 0 and pi. Why? Why is, given any two vectors, the angle between them have to be between 0 and pi? Including, right? Inclusive. So what if it's 0? They're parallel, right? Okay. What if it's pi? They're parallel but point in opposite directions, right? What if it's bigger than pi? Well, it's smallest angle. So now instead of talking about this angle, you're now talking about this angle. So theta is the smallest angle between the two. But it's restricted between 0 and pi. Now consider the cosine function from pre-cal. If you're between 0 and pi, cosine between 0 and pi looks like what? What does the cosine function look like between 0 and pi? Cosine starts out, and then it goes, where does it go through? What's cosine of pi? Let me break it up a little more. Right there? Between 0 and pi, though, that's what it looks like. Now, it continues like that. Agree? Okay. When the angle is 0, we have cosine as 1, right? Angle 0. Cosine of 0 is 1. Then look at what that theorem tells us. Sorry. If theta is 0, cosine is 1, and then this right here, cosine of 0 being 1, just turns it into this, doesn't it? So if I say, what's the dot product of these two vectors right here, as they appear in front of you right here? What's the dot product of those two? Geometrically, what is it? What is this? The magnitude of u, so the length of u, right, times the length of v. So if they're parallel like this, right, pointing in the same direction, then the dot product just means you're looking at the product of their lengths. That's all it is the product of their lengths. Now, if the angle is pi over 2, right, what's cosine of pi over 2? 0. And therefore, this becomes 0. And the dot product is 0. Now, I have this like bunch of exclamation points here, not because my key got stuck, because this is a big deal. All right? If I have two vectors, one way that I can determine whether or not they're perpendicular or not is to take their dot product. If the dot product of the two vectors is 0, I know they're perpendicular. Now that'll come later. I'm going to have it up here in terms of a theorem, but for now, that's why. Does it make sense? Oh wait, actually I put it right here. So if u and v are orthogonal. Orthogonal is a word we use synonymously with perpendicular. If and only if u dot v is 0. If and only if. What does if and only if mean? What's the difference between me saying if and only if? We'll talk about it real quick. If x is 2, then x squared is 4. Do you agree that's true? If x is 2, then x squared is 4. Yes? How about the other direction? If x squared equals 4, then x equals 2. Is that true that way? No, because x squared being 4 means that x could be negative 2, couldn't it? So when you say if something is true, then the other thing is true, this direction, right? That's one thing. To say it the other direction might mean something completely different and may not be true. Whenever you see something like this, if and only if, that means it works both directions. That means your implication works both ways. So whenever we're here, so this one right here is not an if and only if statement, all right? But this one is. It says that if two vectors are perpendicular, their dot product must be 0. Or you could read it the other way around. If the dot product is 0, then they must be perpendicular. It goes both directions. Does that kind of make sense to y'all? This is a logic, a little exercise in logic. Can anyone else think of an if and only if statement that would work both directions? Can someone give me an example of an if and only if that would work both directions? How about this? X equals 2 if, sometimes we use if with 2 F's on it to mean if and only if. If and only if x plus 1 equals 3. How about that? Is that an if and only if statement? Okay, let's try it. If x is 2, is that true? Yes. Okay, if that's true, is that true? Yeah, because you would solve that for x and you would get what? 2, right? And it's a unique solution. That's an if and only. Now that's a very cheesy if and only if statement, but it's the idea of logic compared to the one we did up there. Does not work both ways. All right. Now, what if our angle is between 0 and pi over 2? So we know right now that if this is the case, then the dot product is the magnitude of the lengths, or the magnitudes multiplied. If it's this, it's 0. But what if it's anything in between? All that this result says is that if it's between, then cosine is positive, right? Because back here on our picture, if you're between 0 and pi over 2, your cosine of anything in there is a positive number. And so you're taking a positive number, and you're multiplying it times the length of the two vectors. The length of the two vectors should be positive, which means that your answer is going to be a positive number. No matter what, right? Positive times a positive times a positive should give you a positive. Agreed? But what, okay, now what if it's bigger than pi over 2? Well, now your cosine is what? Negative. And therefore you'll have a positive times a negative, which means you should get a negative number, which means that you'll have some negative answer. We can't really say what it is necessarily. We can just say it's positive or negative. So here's I just have two vectors here, right? See them? The angle between them right now is this angle, right? It's less than pi over 2. Therefore, the dot product should be a positive number. And here's the actual dot product. If I make this one shorter, it should get smaller, dot product. What will happen if I start dragging it down here? Eventually, it's going to go to 0 because they'll be perpendicular, won't they? Right around in here. And then once I go past pi over 2, 90 degrees, now my dot product is negative. So Dot product does actually tell you quite a bit about the two vectors and the geometry of them. You know, if you move them around and you say, hey, the dot product came out to be negative, I know that that angle between them is obtuse, larger than pi over 2. What if it's all the way around, 180 degrees, pi, exactly pi? What is it? What does the dot product represent then? If it's pi. They are parallel, but what is cosine of pi? -1. So you have length of u times length of v times -1. So it's their lengths multiplied and then negative, which is the opposite of this scenario, right? All right. So here's an example. Whoa. If v is, if the magnitude of v is 7, magnitude of u is 3, then what's u dot v? We'll start with that one, then I think I'm going to do something a little more interesting. So if I want to find u dot v, I just go straight to that formula, right? Magnitude of u, magnitude of v, cosine of the angle between them, which would be 3 times 7 times cosine 31 degrees, which would be 21 cosine 31 degrees. Which you could find the exact or an approximate answer using your calculator. Just make sure you're in radian mode, right? Degree mode. Because it has a degree symbol, right? If there's no degree symbol there, you're in radian mode. All right. I would like for us to do something a little more challenging than that. Just to kind of warm you up a little bit for the take home. Let me see here. This is not in your notes. I'm just kind of making this up. That means it's a square, okay? Let's say that I have diagonals that go like this. And let's say that this side, this right here, is u. The vector that goes here to here, like that. Can you all tell where that vector is? And let's say that this is the vector v. And lastly, the vector here would be the vector w. And let me just give you one piece of information. Given the magnitude of u equals 1, find u dot v, and then find u dot w, and find v dot w. So 3 things that I want to find here. Everyone good with that? Where would you like to begin? You want u dot w? Yeah, I think u dot w is probably the easiest one here. Right? U dot w would be what? 0. Why? They're orthogonal, right? They're perpendicular. Remember, this vector w can be split up here and pointed right here, tail to tail, not tip to tail. And then they would form a 90-degree angle, which means you're in business. You know, it's dot product of 0. So I'll start with that one. I'm just going to put here w like this, u's like that. This is 90 degrees. 3 dots means what? Therefore. So anytime we write 3 dots like this, that means the word therefore. Okay? So I'm just drawing this geometrically. They're perpendicular. Therefore, u dot w equals 0. Okay? That's it. Hey, I forgot to mention on your take-home test, I don't know why I didn't do this, you need to show all your work. Okay, in detail. Part of the way I grade is if I can make sense out of your work. Okay, I have to be able to follow it logically, step by step. All right, I will give you plenty of partial credit if you make sense. All right, but if it's just answers, I won't give you any credit. And if it's a bunch of stuff I can't make sense out of, you won't get much credit. Even if the right answer is there, if I still can't follow your work or logic or process or steps, then we'll have issues. All right, next, you will be able to drop one of your tests, your take-home exams. 1. You should have 8. Yeah. So you'll be able to drop your lowest. I had a couple of students last semester who they got to a point where they had a couple of other exams in other classes that just really, they just didn't have time. So they just decided to skip one. They just didn't do one, which is fine. All right, which one do you want to do next? UV? Okay, let's talk about U dot V. U dot V. Well, let's draw it first. We have to go tail to tail, don't we? U looks like this. Or sorry, V looks like this. And U comes out like this, doesn't it? And the only way I can really dot these two together is if I know their components, right? Or if I know their lengths and the angle between them. Think about that. What have we learned about dotting things? Here's one way to dot. You've got to know the lengths of both the vectors and the angle between them, right? What's the other way to dot? This, right? Multiply the two components, first two components, add together the second two. So you have to decide in this problem, is it better for us to, or easier for you to determine their lengths and the angle between them, or is it easier to try and figure out their components? If you do components, then you're going to have to find, you know, some origin where you can work with respect to. So what do you think is easiest here? Do you know how long U is? Yes. I was given, right? The length of U is 1. Were you given the length of V? Not directly, right? Not directly. But you could look at this as being, is that a right triangle here? Or could you get it some other way? Do you know the length all the way across? Well, you know this side, right, is 1, because it's a square. This side's 1, which means this hypotenuse would be square root of 2. And then half of that right here would be root 2 over 2. So you do know that one, don't you? So this is root 2 over 2. So you know its length is root 2 over 2. And do you know the angle between them? Yeah, this is where we have to be careful because of the way things are pointed. Okay, your instinct may be saying, hey, there's the angle between them, right? Right there, that's theta. Right there. But look at the way I drew it down here. You have to go tail to tail and look at that angle. Not the way they're drawn here. Tail to tail and find the angle. So what's the angle tail to tail? 135. 135. So this angle here is 135. So I think we can use that formula, right? Length of u times length of v times cosine. So u dot v should be length of u times length of v times cosine of 135. What's cosine of 135? Negative square root 2 over 2. So length of u was 1. Length of v was root 2 over 2. And then this was negative root 2 over 2. Is everyone comfortable with how I got the length of v being root 2 over 2? If you're not, just circle it, we talk, okay? Cosine of 135, negative root 2 over 2. We multiply that all together. What do we get? Negative half. Now, because the dot product came out negative, we should be thinking, okay, the angle between them should be bigger than pi over 2, right? Negative, when you get a negative dot product, the angle should be bigger than 90, which it was, right? So I feel better. I feel good about that result. You all okay with this? Now, what about v dot w? Yeah, v dot w, when we look at these two, here's v, here's w. When I attach those tail to tail, it would look like this. I'm out of room. Can I move on? Oh, wait, no, I'm not. V dot w. It would be, here's v, and this time w comes up like this. Does everyone agree with that? Now, what's the angle between them? 45. So now you can use the 45, not the 135. And the lengths are still the same, right? Length of w is 1. Length of v is still root 2 over 2. So v dot w will be equal to length of v times length of w times cosine of the angle between them, which is 45. This is root 2 over 2 times 1 times root 2 over 2. So this time you're at positive 1/2. So take a moment, look at your mini exam. I usually don't give this much guidance, but look at your mini exam. Number 2. This problem is pretty much the same concept. It's just the geometry is a little harder. I mean, this is pretty basic geometry here, right? To know that this angle would be 45 degrees here, right? It's the same sort of thing. Okay? All right, let's get on. Checking for orthogonality. How can I check to see if two vectors are orthogonal? Take the dot product and hope for what? 0, right? Dot those two. What do you get? Should I find the length and all that? No. No, just dot means, in this case, take this 2 times the 6, which is 12, 4 times the negative 3, which is negative 12. Add them together, you get 0. Yay, they're orthogonal. If U is 2, negative 2, 6, and V is A, 3A, negative 2A, then find A such that these are orthogonal vectors. I think I'd like to change this problem a little bit. I'll do it when I write it down again. And I'm kind of doing this on a whim, so I don't even know if the math of this one's going to work. Let's see. Let's try it. Let's change this. Instead of it being U is what they gave us there, let's make it 2A instead of just 2, negative 2, 6. And let's make V A, 3A, negative 2A. I would like for you to tell me if there's an A that I could plug in here and make these two vectors orthogonal or not. So what are we going to have to check? What do we need to satisfy for them to be orthogonal? We need the dot product to be 0, right? So what is the dot product? So we take 2A multiplied times A is what? 2A squared. Then we do negative 2 times 3A, which is negative 6A. Then we do 6 times negative 2A, which is negative 12A, equals 0. Do you all agree with that? And that's just 2A squared minus 18A is 0. Now what? Factor out. I'll do a 2A, even though you could have just done A. Which means what? A equals 0 or A equals 9, right? Two possible solutions. Now, let's just see, though, what happens here. If A is 0, we get the 0 vector, don't we? And it's kind of weird because the 0 vector, technically, you could try and say is orthogonal to everything, isn't it? Because it dots to 0, right? But we don't like to consider the 0 vector when we're talking about orthogonality because it's kind of trivial. It's not even really a vector. It doesn't have length or anything. So we'll scrap the A as 0 and just go with A as 9. Now take a look at exam number 3, mini exam 1. I call them mini exams. Number 3. Find the value or values of B which make these orthogonal. It's pretty much like this problem here. That's the one I said you couldn't use a computer on. The challenge on that problem is purely algebraic. It has very little to do with calculus. It's just, can you solve an equation or not? The equation you're going to get, look at the first multiplication on that dot product. B times B cubed, right? It's B to the 4th. So you're going to be looking at a 4th degree polynomial, trying to solve it. See how you do. All right, dot product theorem, further results. So because we had that equation, we can come up with this formula. It's actually quite easy to deduce that formula. If you just take what we knew, u dot v equals magnitude of u, magnitude of v, cosine theta. If we divide both sides by magnitude of u, magnitude of v, they're gone on this side, assuming neither one of them is zero vector. And then take arc cosine or inverse cosine on both sides. When I take inverse cosine of cosine, right, that should just leave me with the theta. And that's what that formula you have in front of you is, right? You have theta is arc cosine or inverse cosine of u dot v over magnitude of u times magnitude of v. The nice thing about this is if you have two vectors, you can find their angle now. You don't need their angle. You can actually get their angle by just knowing what their dot product is and then knowing what their magnitudes are. So find the angle between these two vectors. So what are you going to need? Their dot, right? The angle will be arc cosine of their dot divided by the product of their magnitudes. So let's get their dot. What's their dot product? 26? It's negative 6 plus 28 plus 4, which is 26. All right with that? And then we need each of their magnitudes. So what's the magnitude of u? Square root of the sum of the components squared, so 4 plus 16 plus 16. 6. Square root of 36, 6. And then magnitude of v, could we be so lucky to have a nice one there? 9, 49, and 1. Root 59. Right? So here's where we are. The angle is arc cosine of 26 over 6 root 59. And you could reduce that fraction, right? 2 goes into each of these. But let's get an approximate answer on the calculator. Let's actually figure out what this is, do arc cosine of it, so we can have an approximate angle. And make sure that you know what, if you're in radians or degrees, when you give me the answer. What do we got? 55.66, any seconds? And that's degrees? Okay. So if your calculator was in radians, you could put the radian answer in here. Just don't put the degree symbol. Or convert it to degrees, approximately. So that's how that works. That's kind of, you have a problem similar to that on number 4 on the test. I give you this thing called a parallelepiped. It's kind of like a shoebox that's been parallelogrammed over a couple of times. And I've got 2 vectors in that box, and on part B it asks for the angles between them, between those vectors. So something similar you will have on your take-home thing. Are these orthogonal, parallel, or neither? So how could you check real quick to see if they're orthogonal? Dot them up. So if I dot them up, you get what? 2 times -4, it's -8. -2 times 4 is -8 again. 6 and negative, no, that's not going to work, right? So they're not orthogonal. How about parallel? Yes? How are they parallel? Yeah, you have to notice that this second vector is a scalar multiple of the first vector. If I multiply this vector u by -2, I get this, don't I? All you have to look for is a common ratio between the components. Just take -4 divided by 2, you get -2. Take 4 divided by -2, you get -2. Take -12 divided by 6, you get -2. If you have a common ratio between all components, then they're parallel. The vertices or corner points of a triangle in three-dimensional space are given. Determine if this is a right triangle. Now we're starting to get to some more interesting problems, I guess. So let's say we have, these are the corners of a triangle, right? These are not vectors. These are the corners of a triangle. Now, I do not need to draw an accurate picture of this triangle. I just need to realize that it is a triangle sitting in three-dimensional space. And I will just label these. I don't even really care which is which. And what I'd like to know is whether or not this is a right triangle or not. I don't know that. With my drawing, it doesn't look like it, but it could be, right? So how can I determine if it's a right triangle? In order to be a right triangle, we need one of the angles to be 90, right? Or in other words, we need, if we look at the sides of these as vectors, we need the vectors to be orthogonal. Agreed? So let's just check this one right here. Let's say this angle right here, I'm going to call that theta. Let's call it theta 1. That angle theta 1. Now, I have to create from that two vectors. Call this one u, and I'll call this one v. That's the vector that goes from here to here. Whoa. Now, be careful here. Both tails are at the vertices, or the vertex of this, right? Right here. So u and then v. What I need is for that to be 0 when I dot those two vectors, right? In order to show that it's a right triangle. But I have to create those vectors first. I haven't created them, have I? What's the vector u? It's the vector that goes, from here to there. So we did this in the very beginning. That's the vector what? Remember, if we're going to go from here to here, I take this, subtract from it this, right? 2, take away 1 would be 1. And now I'm angled brackets, right? And then, careful, 0 take away -3 plus 3. And then 4 take away -2, 6. Okay? The vector from here to there is that. What about the vector v? -7, 1, -3. Now, let's dot them. Okay? Let's dot them. What's u dot v? -7 plus 3 minus 18, which is not 0. And so I know this is not a right angle. So can I say it's not a right triangle? No. I need, for a right triangle, I only need one angle to be right. So now what do I need to do? Check this angle. To check the other angle, I'll call theta 2. I need to create two new vectors, don't I? Or there's different ways you can approach it, but I need to be looking here, right? Technically, and I could flip V over, but I need to be looking there instead, don't I? The angle from here to there, the angle from here to here, and then dot those and see if I get 0. And if that doesn't work, then I have to do the third one, right? You think you could do that? You understand it? I won't finish it, but that's the idea. So checking to see if it's a right triangle or not. Still have half an hour. Y'all okay? I think what's going to be kind of crazy with this class this summer is just the amount of information that's going to be given to you on one day, and then the fact that we're going to turn around and then cover another 3 sections the next day. It's a lot. A lot. And I know for some of you, this stuff is still review and stuff you've seen before, but it's going to pick up pretty quick, and that'll be the challenge. When I decided to offer this class this summer, I was like, I don't know if this class is going to make, who takes Cal 3 in the summer? 28 people, and we have people who want in the class still, so, Okay, vector projections. This very important concept is going to pop up throughout the semester. I'll be like, oh, remember when we talked about vector projections? Or this right here. It's very geometric, and so I like it because I can kind of make it make sense. We'll see if this goes in or not. The example I'm going to show you is in 2-dimensional space, but the whole idea extends into 3, all right? Given 2 vectors, we can project one vector onto the other. Look at it as casting the shadow of one vector onto the other. The cast shadow represents a new vector, which we will call the projection. So here are 2 vectors. Kind of difficult to make out the colors here, but does everyone see this is like a red vector? This is a blue vector, and then they've got this is supposed to be purple. Do y'all see that one right there? Oops. Okay, right now what we're doing is we are casting the red one, projecting the red one onto the blue one. And it's almost like what we've done in the past called dropping a perpendicular from the red one down to the blue one. So imagine drawing a line that connects the tip of the red one to the blue vector, but that it comes in perpendicular. Wherever it intersects, right here, is the projection, the shadow. So it's like the light source is coming straight down like this. Y'all see it? So would you agree that that purple vector, which is the projection of the red one onto the blue one, is parallel to the blue one? And therefore it is a scalar multiple of the blue one. Okay, what if I take the red one and I start moving it this way? That projection is getting smaller and smaller, right? The vector is getting smaller, still parallel. What will happen if I go past 90 degrees? The projection will go the other direction. Now, this is the thing that people have trouble with, I guess, because they're like, well, wait a minute, hold on. This blue vector is over here. The red one's not projecting on it, right? Well, technically it's not projecting on it, but it is projecting down to an imaginary line that goes through the vector, isn't it? And so that does still give you a projection vector, it's just pointed in the opposite direction. So you can still have projection even though the angle is greater than 90 degrees. Make sense? Now what if we do it the other way? What if I cast the shadow the opposite way? I go the blue one onto the red one instead. Then it looks like that. Notice the difference between these two. There, right? See, your perpendicular is different. So you're projecting blue down onto this one. In this case, this vector is parallel to the red one, right? It's a scalar multiple. If I make this blue one go backwards this way, what if they're orthogonal? You get the zero vector, don't you? And then it goes the other direction. Okay, vector projection formula. So I had already said that the purple vector is a new vector, right? It's created from the other two. We can use these formulas to find the vector and to find its length. So given two vectors u and v, the vector, which is a projection of u onto v. Remember, we could go both ways, right? I go v onto u or u onto v. In this definition, I'm going to go u onto v. It is called the vector projection of u onto v. It is denoted, or the notation we use is projection PROJ, with the subscript here of the v vector and then the u vector here. So you can kind of see it's like this is u onto v, right? U onto v. V is the smaller one. You're going u onto v. And here's the definition. Here's the actual formula for it. It's v dot u over the magnitude of v squared times v. And I ask you to look at this part right here. V dot u, when you dot two vectors, it spits out a what? Scalar, right? So this is a number, right? Divided by the magnitude of a vector is a number, right? Squared number. So you have this is all just one big scalar times v, which means that this is a scalar multiple of v, isn't it? And that's what we said. If you project u down onto v, that purple one is a scalar multiple or parallel to v. So that's your scalar multiple of v. As expected, that's what I say down here. Now, of course, since that vector, the purple one, is a vector, we could ask to find its length, couldn't we? Given any vector, we can find its length. Well, this is a nice, cleaner formula for finding that length. Instead of having to go through and find the projection and then its length, just use that formula and you get the length straight away. So it's the dot product over not, notice we don't have that v next to it, and this is not squared. So if you just compute this, that will give you the length. And that is called the component of u onto v, or called the scalar projection. So this one, this is the vector projection. Vector projection down gives you a vector. The next one, we call the scalar projection, gives you a number. It is the length of that projected vector, or the component of u onto v. This is that same demo that I showed you just a second ago, but it's actually computing some things here. So again, the difference between the projection vector and the scalar projection. When you do the projection, it spits out a vector. When you do the scalar projection, it spits out a number. That number is the length of this. Look at the length is negative. That's because it's pointed in the opposite direction. This will probably be it. We'll wrap it up with this example here. Okay, let's see here. We're going to try and find, I'm doing example, I'm going to do example 10, example 9. They're almost the same. I switched the projection. Do y'all see that difference between example 9 and 10? Do y'all see the difference? 9, it's projection of U onto V, right, and component of U onto V. Example 10, it's V onto U and V onto U. So same problem, switching which vector goes onto which. So I'll do 9. So for number 9, U is given to me to be 2, 4. V is given to me to be -3, 7. So what is the projection of U onto V? So the formula for that was V dot U. Could I have written U dot V? Yes, because it's commutative. Over magnitude of V squared, and then V, right? That's the formula. So what is U dot, or V dot U? -6 plus 28, so 22 over, what's the magnitude of V squared? So magnitude of V over here was 9 plus 49, it's root 58. Y'all agree? So I get root 58 here. And then what's V? Well, V is just -3, 7, right? Angle brackets. See, this is the scalar multiple. Yes. Where? Oh, yeah, I need to square it. Thank you, thank you. And then, so whatever this is, right? Scalar multiple of this. 22 over 58. Let's just reduce it. Let's not get a decimal. What is that? 11 over 29. Then -3, 7. So then what we do is we distribute, right? That's a scalar, so you get something like -33 over 29, angle bracket, and then 77 over 29. So that is the vector that represents the projection of the U onto the V. Should be pointed in the same direction as V. It's actually a little bit longer or shorter than V? It's a little shorter than V because 11 over 29 is smaller than 1, right? So it's a little bit shorter than the V vector. Now, the component. I know we could get the component right now by just taking the length of this, right? But let's just start from the beginning and use that formula one time just so we can see it. Because a lot of times you'll want the length, but you won't care about the vector. Other times you'll want the vector, but you won't care about the length. So let's just act like we wanted the component of U onto V. So the formula is pretty much the same, right? V dot U, but this time over magnitude of V, and that's all, right? Which is 22 over, this time, root 58, right? Which we could get a decimal approximation to, but we won't. We'll just leave it. Let me see if there's anything else here. Service area. So technically speaking, you can do, I've talked about everything to get you through every problem on the take-home except 4C and number 5. Well, I guess what I'm getting at is this. You should be able to do everything through 4C, no, 4B, everything 1, 2, 3, and all the way up to 4B with just what I've gone through so far. 4C, I still need to talk about volumes, how you can find volumes of things with vectors, and I haven't talked about surface area either, so number 5 would be, I would not encourage you to start number 5 yet. It can be done without anything I've done in this class, but number 5 is a lot easier if we just go into the next section a little bit. Okay, so it's 4:15. What other business? Anything else we need to talk about? Homework, I will post a homework assignment on Canvas. Just check your email. And if you have any questions on how to get to that email, let me know. Yes? I'm thinking I'm going to try and just keep us in here because the projector here is a little better than the one over there. But we'll rearrange because I don't like that situation there for you, having to turn like that. So, okay? All right. Everyone have a good one. See you Wednesday.